Hello.
Hello.
Hi, how are you?
Okay.
Okay. Jesse says he's double booked. Well, let's just go ahead and listen. It's fine. So how was everyone?
Yes,
Oh, was
he
that?
has 2 ears. He has 2 ears.
Yeah. All right. So how was everyone today?
Okay.
All right.
Looking for tomorrow. Tomorrow I've got a cataract operation.
Oh, yeah. Good luck.
Okay.
Yeah.
What?
Good luck.
And I'm up late today, so you're not going to see me.
Yeah. Sushmanth, how are you?
I just want to give my update. We are having a rain here, heavy rain, so there are some kind of power outages and work issues.
Okay.
I couldn't attend the meeting through my laptop, so I thought to come and just give a little update on my last week work
Yeah, I
and
got
mention you some points. I don't know when my phone gonna switch off or not. By next week I will be prepared for this meeting and all. This is like all kind of sudden it came, rain and also. First thing to mention is this week, as coding began, I started working on the model, cell segmenter model. I was using segmented models.pytorch library as mine used for segment anything, integrating with segment anything. But as segment anything was in initial phase, there are a lot of bugs in their library and the model was not learning at all. So I tried to use that library only. I fixed some bugs, but that's not, there are a lot of bugs I couldn't solve. So I thought of not using that library and I want to do my whatever fine tuning the model in a classical methods. So I will be till last week I have done that only, solving the bugs. I was trying out error and trial whether it works or not, but it is not at all working for the small models also. So I started using classical method like general using nn dot module from PyTorch to fine tune the model. From this week, I will be start coding of that for cell segmenter and membrane segmenter. And I will try to host them in Hugging Face also. After that, next 9 weeks, I will completely focus on DevoNet. As the dataset was ready and everything is ready, I was using cell tracking challenge dataset to train the DevoNet model. It's absolutely fine because it has the ground truth images and the segmented images and the dot images representing the where the cell position is there. It would be a perfect data set to train that model. So I have already coded the model, but I just need to train it on. So I will be next after these 2 weeks, next 9 weeks, I will completely working on that and write a paper on it, like how to use it completely like DevoLearn. I have to write unit tests also. So I will start working from this week itself. I will give you update in next week. Actually, I wrote a blog about my community bonding period also. I have posted it in my website. I have shared it everywhere, and that's what it is. Every week I will write a blog. Week one, by tomorrow evening I will post it, and I will give you in the DevoLearn channel. And I was pushing them into DevoLearn blogs also, so everyone could read it.
Well, that's great. Yeah, thank you for that.
Sorry for all this mess. I mean, it's kind of sudden it happened. I don't know. I don't have this inverter kind of thing. So from next week I will be get prepared and attend meetings in perfect way.
Okay. Yeah, that's fine. Well, thank you for the update. I did get your message in the Slack channel, so I did look that over, and then I saw that you had a post. So why don't we look at that now? I'll put it up. Let's see. Here we go. And so, yeah, this is Sushmanth's blog. He says he's putting this up at DevoWorm or DevoLearn, the blog that they created before the community period as well. So you can go from the DevoWorm.github.io site, and you can find it through there. So this is his post on community bonding. This is kind of talks about getting selected for GSoC and working on the project, then talking about C-RNNs, data capturing, folder format and files meaning a data set, data analysis, which is this part. Instance segmentation, and continuing weeks commitments. So this is just kind of like laying out the next steps. So that looks pretty good. Let's see that. Okay. Yeah, so you have your...
I will try to write it more. I wrote in very small, like I was thinking to write commented code in the blog itself, explaining what all code is doing exactly. I will update those also, and I will host a perfect blog here itself. I just need to make small updates which explains the code.
Yeah.
That would be perfect if someone reads in the future also, they can understand what it's and how it is working and all.
Yeah, I mean, that's something you can do like in the code too. I mean, like you can set up a notebook where you can explain some of that. But yeah, I don't know how you put it in the blog body. I guess you could just take screenshots, or there may be some interactive thing. I wouldn't spend gobs of time on it, but to see what we can put together, you can put together pretty quickly. So
okay.
Yeah. And then this is the repository. So yeah, looks like we're got the notebooks in here.
They are not perfectly updated actually. I will update it soon, and maybe by tomorrow I will keep it.
Are you okay? Oh, okay.
I'm sorry, I have told you the line itself, right? Sorry.
Yeah.
There was some thunderbolt. Okay, anyways, that's all my week updates. I will definitely keep the notebooks and the code part in DevoWorm Slack channel. Okay. I'm promising you this won't repeat next week. I will be updating whole thing by tomorrow.
Sounds good. Yeah, thank you. Yeah, that's great. So I look forward to it. And yeah. Were you able? One more thing. You mentioned in the Slack that you're going to meet with Mayok this weekend. Did you get to meet with him, or?
Mike was pretty busy this weekend, so it's not like tomorrow we can have a meeting and solve that bugs. But he was rightly suggesting me that to use classical methods to fine-tune the model rather than using some libraries to segment. That's what his suggestion is. After his suggestion only, I started working on classical methods of implementing this code. So maybe we will have a meeting tomorrow and we will discuss it, and we will keep that update in the Slack channel.
Sounds good. Yeah. Yeah. Okay. Yeah. Thanks. Yeah, and look forward to seeing next week's work. And yeah. Hello, Himanshu. How are you? It's very low.
Hi, Bartley.
Hi, how are you? There you go.
Yeah, I'm fine. Can I share my screen and give you an update?
Yeah, let me unshare mine first. Okay, go ahead.
Okay.
There you
go. Is it visible?
Yes, I can see it.
Okay. Basically I've been maintaining a OneNote which has like all the important stuff in it. Compared to like last year, which I did just one document. It was really hard to get around things.
Right.
So basically, for the community period, I've been looking at all the previous year projects which have been similar to this year's, like the GSoC 2017, 2018, 2019 onwards, and I've been writing some notes about it. like the 2017 project was based on classical methods, as Sushmanth said right now, and it is also something I've been working on. And then the 2018 GSoC was like a continuation of 2017, but it had like some visualizations of the developmental cycles of C-RNNs. And in 2019, there was an unsupervised approach of segmentation proposed. And then in 2020 onwards, it was deep learning based. Like I looked around all the previous projects and tried to get some inference out of it. Also, I've been doing some research on like the problem statement itself, especially the first part of the problem set, that is to like refactor the segmentation code. And I've come across a really interesting paper on the data set we have used. So this is like the cell tracking overview paper. Like it's basically a benchmark of all the 10 years the cell tracking challenge has been held, and it was recently accepted on 13th April, and it was published online on 18th. So it's really new. And in this, I went through the paper and I highlighted all the key points in which like the C-RNNs has been like the dataset which we are using, which has like TIFF files, has been points that have come across regarding that dataset. Basically this diagram over here tells us all the techniques and strategies the teams have used which were in this challenge. So if you look at over here closely, like if unit is something which I wanted to do for segmentation, and as you can see, like around 23 people have 23 teams have done unit, and so on. Like so, it's basically across all the teams, like how they have proposed this challenge. And so, as this is the dataset we are using, like fluoro and 3D HCE, like fluorescence, and it's a 3D dataset, and it's of C-RNNs. So that's the naming convention, I think. And also this also has like all the properties, like a signal to noise ratio, contrast ratio of all the dataset which was already given. Like and this fluoro 2D M-Simplus is what we used in stage 1 of the DevoWorm.
Okay.
Yeah. So basically, I read through this paper, and some of the inferences I came across was like what type of methods are better for which data set, and an approach to generalize the model so that it works on most cell tracking tasks, like segmentation tracking tasks. So one of the main key highlights of this paper was that when we merge all the data sets, like the C-RNNs data set does not perform really well as opposed to other data sets. And the reason behind it is that the data set itself is like a 3D data set, and it has almost spherical objects, and it has significantly higher cell density. So what we come across is that this is the main reason that leads to like that the model is not optimized for this particular data set. Also, one key highlight that I wanted to show was this like the use of a Gaussian bandpass filter for noise removal. So like a bandpass filter is like basically we convert an image to a signal, and then we do processing on it. Like that's the conventional way to do this, and this was kind of an interesting approach. Like they use the Viterbi algorithm, which is like a hidden Markov model algorithm to do the cell tracking, And this lightweight segmentation was like really good. So this is one thing I'm like looking into.
Okay.
Also, they had like some of the codes was shared on this GitHub link, like cell tracking challenge GitHub link. This one, and they had like some Fiji plugins and for all the source code that they have used.
Yeah.
Also, like there are some other papers that I have been reading, like this 3D convolutional neural net based segmentation one, which which also use C elegance and so similar to our dataset, and also the topological data analysis one, which was the main paper that you had given for topological data analysis.
Right.
Yeah. So this is the like the theory part, and then I've been also getting my hand into the actual code. So right now I've just defined a new function like which basically doesn't use some external library like simple ITK to directly load the images into the PyTorch tensor, which we basically use further in training and developing the model. So the previous method which was proposed in previous years was to use a different library, and then you have to read the image in that library and then get an array. Instead of that, we can just use a TIFF file package, which is also like loaded in Colab itself, and then we can just directly load the tensor, and it saves a lot of time because we are calling a display images function a lot of time. So basically, using this, I'm using Google Colab, and then I basically the TIFF. I basically displayed the images, and the main thing is like the TIFF file is clustered into 35 different chunks. So like each chunk just tells us a different time step, like how the cells are in 3D. So 1 to 35, like that way. So this is at 0. The first image is at time step 0, and at t0, and the last image is as t34. This one. So you get like a 3D view from top to bottom, like that way. And this is the ground truth of the fluorescent image as well, like plotted that as well. And then this is basically to see if like which is a better compression. Like PNG does a less compression loss compared to JPEG. And right now I'm trying to do the feature extraction part, like using a Canny image and edge filter. Like edge, I've defined two functions over here, and what I'm trying to do is like to use thresholding, which is like erosion dilation, and then you do the morphology, but it's giving error. Like I was basically doing that right now. It's just a shape error that I'll figure out. But this was the update for.
Okay. Yeah, that's great. So what are your plans for next or this week and the coming week?
So this week I've also been researching on the models that use like the unit one, and there's also a deep lab V3 kind of model which is also there in Torch Vision. So like I was doing some tutorials as well. So right now I'm just figuring out like two parts of it, like a model for semantic segmentation and a model for image segmentation, and including both of those, and try to do one of them at a time, and then train it on Colab or Kaggle, whichever is better for G, depending on the G constraints of data, and after that I'll I'll give the update on Slack, and also write a blog on the community bonding period as well as the coding period starts. Like I started, I was working on that, but like it's still not ready yet. So I'll show that as well.
Okay, that sounds great. Yeah, thank you for that. Yeah, you mentioned using models for semantic and image segmentation, and I don't know if you're aware that Sushmanth has been working on that sort of thing for DevoWorm. Like, yeah. So,
can I add?
Yeah, go ahead.
Hello?
Yeah.
I can add some suggestion here. Actually, DevoWorm already has a semantic segmentation model, which is well trained. I mean, it's perfectly fine because ImageNet is a kind of weight file which they have used Mayuk and Minacuse. It is absolutely trained on well perfected data, and it was fine tuned again. So if we can't put I think it couldn't cross the. I think any other model doesn't give best output than that one. Rather than using a deep lab or something like that, see some new models from Himanshu. Actually, there are some pre-trained models came out last couple of months. Right now, I choose segment anything model, which is perfectly fine. Like that, you can see other models which could work fine because deep lab maybe it couldn't give you the best results as compared to ImageNet, which Mayuk and Minuk use. So that's you can't get a loss value below than Mayuks and Minux if you use a deep lab. This is what my suggestion is. And DevoWorm already have a semantic segmentation model. So I don't know would give a best results or not. So let's see.
Okay. Thank you for the advice, and that was my next step, like to look see if I get any better results, or if I can like change the pipeline that which they have given to some extent, so that I can make it better in some sort of way. Like they all like I saw that code also, and even they have used a kind of Gaussian filter only to remove the noise and everything. So I'll look more into it. Also, for instance segmentation, one of the things which was like recommended to use was masked RCNN, like a masked RCNN model. So that is the thing. That is the thing I was going to look at into, because, like as you said, the conventional models which DevoWorm has, they have a deep learning like ImageNet model for semantic segmentation, but for instance segmentation, there is no model with a similar pipeline which was already given. So that is one of the things we can look into. Also, I was looking into the segment anything model as well, and I found some Reddit threads and some good resources which help in inferencing and fine tuning the model to our data set. So I'll share them as well. Thank you for your advice.
Actually, I was doing segment anything model to fine tune. I have found the resources regarding it. I will work with segment anything model. Better you choose any other model maybe, because working on the same model would not give us best results. If you try to compare with another model with segment anything, if we compare both of them and get best results. I have been working on segment anything like past 2 weeks. So that's what my suggestion is. Like you see, other model. My whole project and proposal was completely on segment anything only. And
that's what I was trying to say. Like I'm looking into masked RCNN, but I also, for my own understanding, looked at segment anything model as well.
Oh, okay, cool. Okay. Thank you.
Yeah.
That's great, Himanshu. Thank you for the update. So, yeah, you want to stop sharing your screen, I guess. Okay. So yeah, thank you for the update. Thank you, Sushmanth, for your suggestions. Yeah, we've been working on the DevoLearn, upgrading sort of the capabilities of DevoLearn, and Himanshu is working on these topological data analysis part. And yeah, this, I mean, I want to make sure that we have, we don't duplicate efforts. So I'm glad that both of you can get together. And I would recommend that, you know, going forward is that you kind of, you know, maybe ask each other or see where each other is. You know, we'll have these weekly updates, but also, you know, posting things in the, I guess the DevoWorm channel in the Slack. We can use that to sort of, you know, kind of make sure that we're not replicating each other's work, because that's, if we can use, you know, resources that the other person's using, or if they have recommendations for things, that's good, because it's, you know, it just makes it easier to do things. Yeah. So I look forward to next week and see what people have. And so great. Susan, are you, do you have any updates you'd like to share?
Updates. Let's see. If someone knows how to get a stress strain curve into the yield portion of the curve in COMSOL, please let me know. Otherwise, yeah, I have 2 models working, 3 really, but one was made by COMSOL. And if I could get my stress strain curve to go past the peak of itself over to the other side of things, then I would have a complete curve that matches the paper that I'm working from. So, yeah, I have a paper. Like, I don't know if you can see that.
Oh, yeah.
It has a complete curve. And you put a force on it, and you get data up to here. And that's all fine, but if you go beyond it, there's 2 points, of course, and the program goes fog. Yeah. Give me some sort of unreasonable number that doesn't make any sense.
Oh.
So I don't know what it's doing.
Yeah.
That's my latest.
Okay. Well, yeah, that's a rough spot to be in if you can't figure out from the documentation what's going on.
Yeah, especially unreasonable data.
Yeah.
It's in centimeters, and all of a sudden I'm getting meters, like 60 meters.
Oh.
I don't think so. So that's my issue at the moment.
Oh. Well, yeah, we'll see. I don't know much about COMSOL, like I said, so.
Yeah, it's a program that tries to do everything, and I think that's what's wrong with it.
Right, yeah.
Because they keep looking into it, and there's all these different things you can do with it, and I don't need it to do that.
Yeah.
It's not. Yeah.
That's great. Well, yeah, keep us posted on that.
Yeah, eventually I've solved a number of problems with it already, so this just seems to be the latest, or maybe the final one. I'm not sure.
Yeah.
It's close. I'm getting close to finishing it, but it's just things like that. Is just like,
Yeah.
I don't know. Yeah. So, okay.
Yeah. Great.
Yeah.
So, yeah, thanks for that. So today I'm going to go over a couple things. I'm going to share my screen and let's see where we are with this. So last week we talked about like curvatures in cells and division planes and things like that. I thought that was an interesting conversation. I might get back to that. I did want to talk about some interesting things I've found in active matter and artificial life. So a bunch of things I found kind of at random this week that people were doing. So the first thing is people have been doing some interesting things with reaction-diffusion, morphogenesis, and the things we call Turing patterns. And there's this other sort of variation on Turing patterns called Gray-Scott patterns or Gray-Scott equations. And so this is actually a nice PDE visualization tool. So basically, it's where you have this model, this Gray-Scott model, which is something people have been implementing in web browsers on images. And so this group has been doing this to make visualpde.com, which allows you to explore quite a lot of systems, including beyond Gray-Scott / reaction-diffusion models. This is a picture of Turing, and he's in a background. And with this application, visualpde.com, in the simulation, you can play with the parameters, and it sort of modifies the image. So the background starts to move, and you see things. So it basically, it can reshape the image, or the images. The background moves around a lot. So I don't know if I have a demo of this, if I want to do this in the meeting, but let me see if I can do this. This is it here. Okay, Visual PDE. Sometimes these don't work very well when you demo them, but okay, here we go. So this is the Turing image, and this is the function here. So it's basically doing these partial differential equations. It's implementing them. Here's the equation here. You see that it lists the equations. You have the definitions, so you can modify the parameter values here. The parameters are, I guess you can look them up here. Boundary conditions, you can set those. So right now they're periodic. They can be periodic, Dirichlet, Newman, Robin, and combination. So they're different versions of that, both for U and V. So you can see the U parameter here and the V parameter here. It's part of these differential equations. And you can set the boundary conditions for both. And then the initial condition, which is, so for U and V, you have U, it's 1, and V, it's 0. That's the default. So you can play with these parameters, and you can get, you can make it happen. So let's see if I can run it from here. Okay. See, it's not working well. Oh, see, it's working now. Okay, so well, you see it come to the fore. It's basically a very light image, and it starts to gain some form and then some boundary around the edge of the bust here of Turing. And then you have the edges that are kind of drifting outward, the corners here. So this is morphogenesis of these pixels according to this equation. So that's kind of a neat thing. So, oops, wrong one. That's this tool. So that's the Turing reaction-diffusion, the Gray-Scott equations. Actually, Carl Sim did some interesting work on Turing patterns. There's another tool here on carlsims.com, which is the RD tool. And I'm not going to demo that, but this basically shows you some of the things that you can do with Turing patterns. It's a nice simulator for this. And basically, again, you have these reaction-diffusion equations, these couple differential equations. You can use this to understand. In this case, it's more straightforward biological pattern formation. you get these little cells that form and these patterns over the spatial array. So you can set the parameters like before. It's a little bit different. I think it's basically descriptive parameters in this case, and the equation is under the hood. But they have that tool. This is an example of the simulation running. So let me see if I can get it to run. Yeah, there we go. So you can see that it's forming these cells in the middle. The boundaries are growing. So these boundaries are growing a little bit more. It's kind of zooming in. So, okay. What's going on here? Okay, there we go. So it's doing a lot of interesting pattern formation here in this clip. So you have the scale, scale radial, scale random, and then the flows parameters here. And you can see that it's kind of growing, and these shapes are changing their configuration. So you can see that it's almost like building like a snowflake here from a initial condition. That's fun stuff. So that's great. This again is this is the Turing patterns. This one is animated reaction-diffusion patterns in flagella. So this is a preprint from the Polymaths lab. So reaction plus diffusion equals Turing patterns, right? Well, diffusion of shear plus reaction of molecular motors equals animated reaction-diffusion patterns in flagella and cilia. So these single-cell organisms, they have these flagella that come out the back. And, the same thing can be said of cilia in cells where there are these little appendages that kind of move with, where they can move the organism. They can exert forces on the environment, or they can be pushed, they can be used to modify things if the cell is moving through a fluid or something. So these flagella kind of move back and forth. There's a molecular motor inside the cell, and it's moving the flagella back and forth, and it's propelling the cell. With cilia, you often have like this layer of these cilia that can bend with respect to forces if a liquid is moving through something, or it can be, there can be a stiffness instituted by the cilia or the base of the cilia, and you get all these interesting dynamics. So this is some animated reaction diffusion patterns. I don't really have a demo for this, but there's some really interesting mathematics that come out of this simple mechanism. So this flagella is moving back and forth, it's rotating, and it's generating these waves through the media, but it's also moving forward. And you can look at all those as pattern formation. So you're diffusing shear, reacting. There's a reaction of molecular motors, and this gives you these reaction diffusion patterns. So some really interesting stuff there. This is the paper here. So this is on the bioRxiv. This is the reaction diffusion basis of animated patterns in eukaryotic flagella. So this is by Cass and Bloomfield Gedelia. And they're from the robotics lab. So they're interested primarily in applying this to robotics, but they're doing this in single-cell organisms. So this is the flagellar bead of the bull spermatozoa and Chlamydomonas reinhardti, which is a bacteria. It can be modeled by a minimal geometrically nonlinear sliding controlled reaction diffusion system. So this is, it's one of these systems that generate the patterns we saw in the Turing morphogenesis example, but this is a single cell doing this in a medium. Model solutions are spatially temporally animated patterns. So this is where they're animated in space and time. So if you had like a little, some liquid that it's in, and it's moving across the liquid, it would produce patterns in that liquid from that movement. describing flagellar bending waves, further connecting beating patterns of cilia and flagella with seemingly unrelated chemical patterns from classical reaction-diffusion systems. So there's this basic beating pattern of the cilia, and then there's this chemical pattern from a reaction-diffusion system. And if you add those two together, it creates some interesting pattern formation. Instead of chemical species freely reacting and diffusing in space, so in the examples we saw of the Turing system, we had chemical species diffusing in space and in gradients. But this is where you actually have an active force acting against this background of diffusion to provide these patterns. And so our system describes the tug-of-war of reaction kinetics of molecular motors that are anchored in the flagellar structure, but the shear deformation that they generate can diffuse away via the bending elasticity of the flagellum. So they're actually looking at some of these aspects of shear deformation and some of these aspects of reaction kinetics. So there's an interaction there. Synchronization of the reaction kinetics and neighboring elements occurs via a sliding control mechanism. So this is this mechanism they'll describe in the paper. We derive from first principles the reaction diffusion basis of animated patterns and show that this is a direct consequence of the high internal energy dissipation by the flagellum relative to the external dissipation of the fluid environment. So there's this dissipation of the flagellum. It's moving against the medium, and it's moving the cell, and it's producing these forces into the liquid medium. And then there's this, so that's energy dissipation away from the organism and the flagellum, but then you have this external dissipation in the fluid environment. So that energy has to go somewhere in the fluid environment. By fitting for the first time nonlinear large amplitude solutions of a specific motor cross-bridge reaction kinetics. So this is having to do with the motor itself and the formation of the motor and the reaction kinetics that result. We show that reaction diffusion successfully accounts for beating patterns in both the bull sperm and the Chlamydomus model. So they have like a regular genetic background for this organism, and an MBO2 mutant, which I guess knocks out some aspect of the flagellum's function, unifying these distant eukaryotic species under the same minimal model. Our results suggest that the flagellar beat occurs far from equilibrium in the strongly nonlinear regime, and that in contrary to conclusions about small amplitude studies, a unified mechanism may exist for these dynein molecular motor control. So dynein is a protein that involves that's key in these molecular motors, and provides some of the production of power and motion. So that is regulated by axionemal sliding without requiring curvature sensing or the fine-tuning of basal compliance, and only weakly influenced by hydrodynamic dissipation and the cell body boundary condition. So they kind of go into some of these things. They talk about reaction diffusion models, and then they talk about the Belousov-Zhabotinsky reaction, or the BZ reaction, which is a chemical reaction that can form patterns as well. They talk about other non-morphogenetic reaction systems in 6 and 7. And so there's, I don't know if 6 will come up. I'm interested to know what it is. This is actually spatial patterns in ant colonies. This is a group of people who've worked on swarm intelligence and things like that. So that's an interesting paper. They consider that to be non-morphogenetic pattern formation. And then 7 is dissipation and displacement of hotspots and reaction diffusion models of crime. So this is like human behavior and pattern formation. So they're kind of linking that to some of these other forms a pattern, chemical pattern formation. Let's see if I can get up to the top here. Where we were. Okay, so they make a point here. Oscillations can persist if a smaller part of the system is isolated without diffusion. So this is where if you can isolate a part of the system without diffusion, you can have these oscillations that persist. Coupling the isolated parts via diffusion can entrain oscillators with non-trivial phase differences. So you basically, around that oscillator, you can isolate the system. You can get these oscillations to persist, and then when they get coupled back together, you can get these interesting patterns. This drives, for example, intricate spiral waving patterns in the Bezier reactions, and they have a reference for that. However, despite the universality of reaction-diffusion systems that describe a bewildering array of patterns across science, it is still unclear whether reaction-diffusion theory can be expanded to animated non-equilibrium patterns in nature, such as spatiotemporal patterning of self-organized shape-shifting structures, the archetype of which is the spontaneous beating of eukaryotic cilia and flagella. So they kind of get into, that's why they picked that model system. This is an image of pattern formation via reaction diffusion. So there's this generic reaction diffusion here in A, which is where you have this white and black gradient that come together. And as you know, white is diffusing, black is diffusing. They're coming from opposite directions, and they start to form sort of an interaction. So there's like this gray region here at the top, and then there's this pattern where there are dots, and then there are these kind of these sort of nested tracks that you see here, and then you see dots, and then less dense dots, and then finally you get to the black. So this whole region of interaction forms different patterns based on the presence of black and white and what's going on there. So, and then of course you have zebra stripes during development, so those get assembled via a similar process. This central striped region here in the top image is similar to the stripes you see in a zebra. And so that means that there's like this interaction of pigments that goes across the skin of the zebra that form these patterns. And so such animal markings motivated Turing when deriving his model system. Animated spatiotemporal patterns in eukaryotic flagella is in B, which is here. So this is the cell body, and this is the flagella coming out the back. And you can see that they're kind of animating the movement. So it's moving back and forth. And there's some really complex dynamics of this flagellum as it's moving. So it's not just moving back and forth in a deterministic manner. It's actually, it's almost like a multi-jointed oscillator where you have different components of the oscillator moving back and forth. And you get a lot of really interesting dynamics coming out of that. And this is kind of a model of this, where these dynamics here form these striping patterns. So when they talk about the pattern formation of the oscillator, this is what they're referring to, these stripes. And these are kind of comparable to what you see here in the reaction diffusion model. This is C-RNNs, where you get these two different versions of movement. So the beating patterns of human, bovine, and sea urchin spermatozoa are shown at the top there, along with the breaststroke of two flagella of the green algae. And chymograph shows spatial temporal stripe patterns. This is what the chymograph is here. And then we show it can be modeled with reaction diffusion dynamics. So that's where they're going with that. They wanted to show the compatibility between those two models. Then, you know, they have their results. They have this model here where you have this, this is the axonemal projection So this is where they have this, so this is a cross-section of the flagellar axoneme, which generates the forces needed for this flagellum to move. They have this self-oscillating element, which is where you have a two-dimensional projection of the axoneme here, where you have the flagellum here and the cell body, and it's moving in different directions, and it's showing the associated forces with that. And then you have these parts that are connected in parallel down the flagellum, and then those articulate with one another. They move, so it's like a jointed system. So it is like a complex oscillator with multiple parts, and it propagates this wave going outward. But because this thing has a lot of complex dynamics, that wave propagation isn't linear, it's nonlinear. So you get these nonlinear waves that result from swimming forward. Just basically swimming forward, generating forces using this mechanism. They can generate a lot of nonlinear waves. Those things interact, and they give you the pattern formation that you see in the media. So that's an interesting paper. So that's the part on pattern formation. Then I wanted to talk a little bit about particle Lenia, which is a platform there's a platform called Lenia. It's a artificial life platform. People have been using it. It's open source, I believe. They've been using it to do like these fluid cellular automata. And so there's some new work on particle Lenia. It's actually out of Google Research, and they've been doing things with looking at these particle Lenia, which are these sort of rounded or virtual organisms that move around a space. Like I said, it's like a continuous cellular automata, and you can do a lot of things with Lenia. It's a very flexible system. I've not worked with it too much, but it's really something if you're interested in a lot of things with pattern formation or other kinds of like collective behaviors. It might be interesting to play with. Particle Lenia is an artificial life form that consists of point particles that simultaneously generate a potential energy field. So the Lenia organisms these are the Lenia organisms, and then particle Lenia is just having these organisms act as particles in a collective system of collective motion and collective pattern formation. So each of these point particles generate a potential energy field, and they try to minimize their own local energy. And so what the point of this is to show that if you have a lot of these organisms in parallel, you can take a couple of parameters, vary their value, and create a huge variety of different creatures. So, this is going to have like this, each particle is going to exhibit morphogenesis. It's going to have an energy field. It's going to interact with its neighbors. And then you can look at some of the diversity of form that results, as well as the collective behaviors. This is a Wikipedia stub on Lenia. So this is sort of an introduction to Lenia. It's a family of cellular automata created by Bert Wang, Chak Chan. It is intended to be a continuous generalization of Conway's game of life. So if you're familiar with Conway's game of life, it's this cellular automata. It's this zero-player game where you have basically the cellular automata that's generating different states that move across the board. So people have used this cellular automata to generate different types of behaviors that they can classify, things like gliders and other types of things that emerge from the interactions on the cellular automata board. And so it's basically a continuous version of the game of life. So you have the cells, which are square and discrete in Conway's game of life. Now they're fluid and continuous in Lenia. So these particles are like those squares. And so they can behave collectively, they can move, and you can characterize this as sort of life, different types of behaviors, different types of morphogenesis and things like that. So as a consequence of its continuous high-resolution domain, the complex autonomous patterns, which can be called life forms or spaceships, apparently, generated in Lenia are described as differing from those appearing in other cellular automata, being geometric, metameric, fuzzy, resilient, adaptive, and rule generic. I'm not sure what metameric is exactly, but Dick, you wanted to say something?
Yeah, metamerism is any structure which is repeated, like backbone.
Oh, okay.
Vertebrae in the backbone, that's called metamerism.
Oh, okay.
Okay.
Yeah. So, yeah, they basically just combine in that way and produce complex things. Yeah, so they actually, the GECO conference, which is Genetic Algorithms Conference, Lenia won the 2018 Virtual Creatures Contest at that conference and received honorable mention for the A-Life Art Award, A-Life 18 in Tokyo. So they've been around that community, and, you know, they're kind of, decently received. So working with Lenia, you know, you can probably convince people that what you're producing is not, you know, people will have fewer questions about it than if you homebrew something and put it together. And so they talk about some of the rules of Lenia. They have these iterative updates, which are usually output states being a pure function of the previous state. Then there are these global rules representing the application of local rules over every site. So it's standard cellular automata stuff. There are these state sets that you use. And then you have neighborhoods as you do in cellular automata. So you have the focal cell and then you have the neighboring cells. And so in Lenia's case, the neighborhood is instead of a ball of radius r centered on a site, which may include the original site itself. So this is the ball neighborhood in Lenia, as opposed to the Moore neighborhood in a regular cellular automata. So it's just like a set of circles. So there's a focal circle, and then there's these cells around it, or these circles around it that form a larger circle. And so the neighborhood vectors are these set of relative positions with respect to any given site. So that's how they implement that sort of thing. So they can implement things like this collective pattern formation in a platform that has interaction rules, and then you get these patterns that form. There are a lot of things I'm not going to get into. Their growth mappings, they do link it to the game of life. And then there's a lot of related work which people have noted. So other works have noted the strong similarity between cellular automata update rules and convolutions. And so this is the type of convolution that we're familiar with convolutional neural networks, or CNNs. And so these works have focused on reproducing cellular automata using simplified CNNs. There's this aspect of the emergence of self-repairing pattern generation, which can be done with Lenia. Gilpin found that any cellular automata could be represented as a convolutional neural network. So, we have these cellular automata. They can be represented as a convolutional neural network. And trained neural networks can reproduce existing cellular automata. So we can do everything we do with cellular automata in a convolutional neural network. And then that has implications for, say, like doing machine learning and deep learning. And so these are the wide variety of species you find in Lenia. It's very hard to see here. But basically, it's these different shapes. You have these, these collective structures. They kind of look like microorganisms or small colonies of organisms, even maybe like larvae or or even worms. So they have these shapes that are very lifelike. And, this relates back to the thing we were talking about before with reaction-diffusion and some of the shapes or patterns you get from that, and also some of the patterns you get from things like the action of flagella. So there's a lot here. And I don't want to, there's this final paper I wanted to point out. This is actually interactive programming paradigm for real-time experimentation with remote living matter. And this kind of talks about some of the things, kind of brings these things together. we've conceptualized a programming paradigm that provides stimulus and sensor control functions for real-time manipulation of physical biological matter. So they're actually creating a programming system for manipulating physical biological matter. A simulation mode facilitates higher use throughput, program debugging, and biophysical modeling. So they have this JavaScript web toolkit, Bioti, that supports real-time interaction with swarms of phototactic Euglena cells hosted on a cloud laboratory. So what they're doing is they're playing with these patterns, they're playing with these collective patterns that are formed. They have a programming language that they can manipulate and interact with these swarms. And, I don't know how, I guess this is just something they're sort of proposing, they're not really, they haven't done a lot of cool stuff with it yet, but it looks like they have it mapped out. So you have, people using their computer, they have this virtual representation of these cells and the swarms that they form or the patterns that they form. They're able to apply, different stimulus control functions, biology sensor functions, application control functions. They do image processing, so they need to process the image of the of what the microorganisms are doing, and that's basically how they program living matter. So they're actually programming this using microscopy, using a programming language, and using different inputs and outputs.
Can I pick your brain for something?
Yeah.
These swarm simulations are usually done in 2 dimensions or 3 dimensions, correct?
Yeah, swarm simulations are usually 2-dimensional, although I think...
Okay, I've come up with a problem which I'd like to call swarms on networks.
Oh, yeah.
Okay, have you seen anything like that, where the swarming behavior is confined to stay on the network rather than 2D or 3D?
Not sure. I mean, maybe some of the ant colony optimization work that people have done is kind of like that. So they do like a lot of time, like, yeah.
What would the network be? The way that the ants follow each other?
Yeah, so you have ants as the nodes, and then the edges are like pheromone trails or interactions between them.
Oh yeah. In that case, the what do you call them? The active units are creating the network. I'm talking about swarm on a fixed network.
I don't know. I mean, there probably is, but I don't know what the reference is. Yeah.
If you see anything like that, I'd be interested. It's actually a computer tomography problem.
Oh, okay, yeah. I'll take a look. Yeah, I don't know if there's anything.
In other words, the motion of each of the what do you call them? The active units is confined to stay on the network.
Yeah.
Okay. The ant problem is not the same because they're creating the network.
Right. Yeah. Yeah, I'll take a look and see what there is out there.
Okay, appreciate that.
Yeah. Yeah, a lot of these simulations are inherently in 2D, but I mean, like the Lenia, and then of course the Reaction-Diffusion.
Yeah, of course, you're thinking of swarm behavior, birds and fish and stuff like that. But,
yeah.
I've come up with a weird problem where the network is fixed, then you can move your units along the network.
Okay.
Okay.
Yeah, I'm not sure how, like in the Lenia case, it's a continuous cellular automata. So we usually think of that as a discrete system where you have cells that just kind of interact, and the interaction determines the subsequent state of its neighbors. So it's like if something propagates, it's usually like this cell interacted with this cell and influenced it, and then on and on. With
correct. You interact with near neighbors.
Yeah, but with
that property I'm preserving. It's just that the interaction is confined to stay on the network.
Right.
Okay, that's what's different. They can still interact across edges of the network, but they can't jump from one to the other. They have to stay on the network.
Right. Yeah, the existing network.
Yeah, it's kind of swarms on a different kind of topology rather than continuous.
Yeah. That's an interesting idea. I'll have to look into that.
Swarms on. I remember the networks of Christmas tree light bulbs.
Oh yeah, I remember that problem. Yeah.
Yeah, in that case, you could think of electrons as the units.
Okay. Yeah.
Okay, and they get to move along the wires, but this is a different problem.
Right.
More serious one.
Yeah. So Himanshu had a comment here. Yeah, so the problem formation of swarm on network seems interesting. Since the interaction leads to the step, then there can be a Markov assumption that the current state only depends on the previous state. Yes, there's generally in cellular automata, it's like a Markov process. There isn't usually a memory. It's just kind of like, that's why you have these patterns that kind of diffuse and they're sort of fleeting. In Conway's Game of Life, you have to have things like gliders that move across the screen and then they disappear. And so you get like this, you have to like be careful, you have to watch the thing, find a pattern and then classify it. They're very itinerant in that way. So, but you could like implement a memory on that. It's just that I think the premise of cellular automata though is that there isn't a memory, because if you have a fixed memory, you end up, basically crowding yourself out. So if you, I know Himanshu's worked with agent-based models. If you have an agent-based model where you have a bunch of agents and they're interacting and they kind of form clusters or something in space, and if they're not like, they kind of, the algorithm converges, so they kind of stick there. And then like you can't move it anymore. Like there can't be any more pattern formation because the patterns are already kind of fixed. They just don't have any room to move. The same thing with like chemical diffusion, where there are chemicals that diffuse and then over time they run out of energy and the patterns kind of either stay, kind of static, or they just kind of dissolve. And so at some point you run out of that capability. And sometimes, having more energy or not having a memory of what came before actually helps you create new patterns. So that's an interesting point. And I don't know like what the answer is there. I don't know if anyone's worked on like memory filled or memory capable cellular automata, but I know that by default they're memoryless. So they're Markov.
Bradley, I think there have been some studies on Markov processes with short-term memory.
Oh, okay.
Okay. And there's another peculiar one, which is processes where the memory is of the previous state. And so you don't interact with the current state of other things, you interact with the previous state of it. And this can drive the system into weird kinds of oscillations.
Okay. Yeah.
Okay, it's certainly, I think it was studied in the 60s in differential equations with time delay between the differentiating part and what happened previously. In other words, the state, the current state, the change in the current state is not dependent on the current state. It's dependent on the previous state.
Yeah. Yeah, it's an interesting thing. And we were looking at that example from the flagella, you have all these nonlinear dynamics that are coming out of the flagella's motion. I mean, there isn't memory there, but there are interactions from previous states. Like, if something moves around, you get these waves that kind of collide, I guess.
Yeah. I guess you wouldn't have memory in this because momentum is not important.
Right. So finishing up on Himanshu's comment, this seems like a good problem for an RL-based approach. Yeah, it would be interesting to implement an RL, like some sort of RL cellular automata combination where, the cells are picking the best policy, and then they share that information with their neighbors or something. Not really sure what that would look like, but it would be some sort of policy learning, and then the selection might be like, my neighbor selected this, and I'll select this as well, and then you see what happens. Instead of rules, because the CAs usually have these rules that they follow, but they're very simple interaction rules. So it's like if your neighbor shuts off, you shut off, or if they shut off under a certain set of conditions, you shut off as well. It's not really that deep in terms of like a function. It's just basically a simple thing that it's just copying behavior. It's not really like in depth. But yeah, I mean, that would be interesting to have that reinforcement learning aspect to it as well. So you'd have this, you'd probably have to have some memory as well for it. But yeah, I don't know.
I'd like to bring up one other point. A lot of these things are very neighbor dependent.
Right.
Neighbor dependency depends on the size of the something like pixels or voxels. Okay. I came up with a method many years ago, which is sort of independent of the local scale, and I called it adaptive neighborhoods.
Yeah.
Okay. An adaptive neighborhood, it was used for image processing, and we're basically calculating the contrast around a pixel versus the scale of the region around it. To make that explicit, suppose ordinarily you deal with a 3x3 neighborhood around a pixel. Okay. What we've made it is 3n by 3n.
Okay.
And then what you do is you calculate the contrast between the pixel and that surround versus size of the surround. And if you calculate that, you get a function which goes to a maximum and then sort of goes all over the place. So what you do is you pick the first maximum and you call that the adaptive neighborhood for that pick. And then you can operate on that by changing the contrast to whatever you want with the pixel. Okay.
Yeah.
So this gives you a scale. It gives you sort of a scale independence from the size of the smallest pixel that you're using for your array.
Yeah.
Okay, because it's picking what scale is best for the local region of that pixel. Okay.
Yeah.
So, and it led to interesting image. We were using it for increasing the contrast in images. There was an old technique in mammography called zero mammography, which was basically a Xerox machine that worked on mammograms, and that's where the idea came from. That the zero mammogram actually worked with the physics of the electrons in the plate that formed the image.
Yeah.
Okay. So what this did is it produced sharper images where the sharpness was related to the local scale. Okay.
Yeah.
Okay. Now I don't know. For agent systems, I'd be curious to see if this had an effect.
Right.
In other words, if an agent depended not on just neighbors, but depending on its adaptive neighborhood, rather than its 3x3 neighborhood.
Great.
Okay.
Yeah, it'd be interesting to see.
It was kind of cumbersome, but it's you went to a 3x3 neighborhood, and then 9x9, and then 27x27 or whatever. Okay.
Yeah.
No. But you plot this contrast versus the size of the neighborhood, and you pick the first peak. Okay.
Yeah.
So it's conceptually fairly. It's not too complicated conceptually, but it's a lot of computing.
Right. Yeah. Yeah, I know we did things with. I don't know if this is. Well, the morphozoic stuff that Tom has been working on.
Morphozoic. I don't think he used adaptive.
No, it doesn't use adaptive neighborhoods, but it uses like a different definition of neighborhoods than you typically see in a discrete cellular automata. So, yeah, it's not really adaptive. It's kind of like nested, I guess. So you have these smaller neighborhoods and these larger neighborhoods. But yeah,
there's adaptive by finding the optimum around each pixel.
Right.
Which of course could change with time.
All right. Well, that's good.
So you might be curious.
Yeah. All right.
Reformulate.
Oh, go ahead.
Yeah, maybe you can reformulate some of these agent problems in terms of adaptive neighborhoods.
Yeah, that would be interesting.
See how they behave.
Yeah. So now I'd like to talk about a few other papers. But first I'd like to do a couple of the demos that I didn't do when we were in the meeting because it tends to lag. So the first one is this Reaction-Diffusion tool. This is the Carl Sims website, carlsims.com. As you can see, we have this pattern that's forming. I showed the movie where you can regrow. So it grows from a circle, and it's growing these fractal patterns throughout the space here. And then the insides of those fractal patterns are changing their shape. And you can see that like some of these interior cells, things are being defined sort of in different ways. So there's definition of, it almost looks like a maze is forming out of those undulations that were originally, that resulted from the circle. So you see this sort of snowflake pattern that's forming. And then you see these deepening furrows that look almost like a maze is forming here from a central point. So this is how this sort of reaction diffusion happens. You can vary the pattern in the simulation. So I can regrow it according to like a stripe pattern. So this is where you start with a single point and then it diffuses across the space. And again, you have these long boundaries on either side, but in the middle you have these dots or these sort of lumps of whatever this is. And it looks like they're dividing. And there's this pulsing in the middle that's sort of where it's just kind of like, there's a lot of, I think there's tension on the surface. So Dick mentioned that, there's a difference between 2 dimensions and 3 dimensions. So what we see here is the 2-dimensional case where we have up and down and left and right. And so it can diffuse across this 2-dimensional space. The forces can act along this 2-dimensional space. So you have this 2-dimensional gradient, basically. You have things happening in the middle, you have things happening on the edge, you have things happening on one side versus another, but it's always a 2-dimensional aspect. And of course, as we know, biology and tissues in particular exist in 3 dimensions. So this is not 3 dimensions, this is 2 dimensions. So the question is, what does a 3-dimensional system like this look like? And the answer is that it may be that it's just kind of a spherical version of this, or it could be very different depending on how far you are in terms of the layering from top to bottom. So, this is how you get pattern formation, say in embryos. You have this local pattern formation that leads to global, heterogeneity, and then you get those systems integrated over time. So, yeah, this is a nice simulation from Carl Sims. This is an example of the Gray-Scott reaction-diffusion system. So the Gray-Scott system is a little bit different from the Turing system. So the Gray-Scott system is a reaction-diffusion system. This means that it models a process that consists of a reaction and a diffusion. So the reaction is some chemical reaction that transforms something. So it's usually some sort of reaction that takes in energy, it produces an output. And so you can see with the expansion of some of these objects in the Carl Sims simulation, where you have this growth, that's going to be a reaction. Your diffusion, on the other hand, is how these things spread across space over time. So it may be chemicals that spread across space over time, or it could be particles that spread across space over time, or it could be a cell that expands and then divides. A number of things that are involved in diffusion. So diffusion doesn't necessarily involve energy, although it could. But in general, if you're diffusing, your energy function usually minimizes from with respect to the distance from the source of that diffuse process. So you might have a chemical source, like a cell, and then as you move further away from that cell, the amount of chemical diffuses until you go to a point where it's almost nothing. And so I can draw this out. So if I draw this out, I have a source, which is a cell, and I have a two-dimensional space where things are diffusing. And that diffusion function usually is maximal at the source of the cell, and it minimizes as it moves away from the cell. So we're considering this diffusion along from left to right here. And so this whatever factor is being generated by the cell, that's an output, and the input, of course, is energy. So there's some reaction in the cell, and then there's diffusion going outward. And you can couple these, through the consumption of energy, the production of some reaction in the cell, and then the fusion of the products of that reaction moving out, finally getting out to an edge where it's almost non-existent. If I look at a system of two cells, you can see where we get these gradients. So if we have a cell on the left and a cell on the right, they have their own reactions. Maybe it's the same reaction. There's diffusion outward. And this is, again, linear diffusion and uniform mostly. So there's a set of concentric circles that sort of, at each circle there's some decay of that product in the environment. And then eventually they come, this decreases almost to nothing. But the important thing here too is that as it decreases to nothing, if they're close enough, there's this region of sort of interaction or overlap between the two products being produced. And so that region of overlap is usually the edge of these gradients. So in Turing reaction diffusion, we often speak in this language of pattern formation, and the patterns are usually stripes. So they look like this, maybe. We have stripes. And the stripes really result from the edges of these diffusion cones, or whatever you want to call them. Basically, as those overlap, those boundaries sharpen, and they produce some sort of striping pattern. So you might have source cells in the middle of each of these layers. Like we saw with the example of the black cell and the white cell, and their interaction. There's diffusion coming from both directions towards this boundary. This boundary represents the intersection of these two diffusion cones, and then that sharpens the boundary between them because they interact, whereas they don't interact if if they diffuse, say, up versus down. They won't necessarily diffuse when you have something like that because they're not coming into contact. Those products are coming into contact at the boundary, and then that's when you get a sharpened boundary, which is usually maybe a change in pigment or like a combination of two chemicals, and you can usually see it as a pattern. So that implies that this process happens in parallel from left to right or right to left. But this is all two-dimensional, and so I think that's an important thing to remember. Now, Gray-Scott, of course, is a model where reaction is a chemical reaction between two substances, U and V. So those substances, in this case, will diffuse over time. During the reaction, U gets used up while V is produced. So this is interesting that you have U and V. U is transforming maybe into V. U gets used up, so there's a stockpile of U, and that gets used up in producing V. And V might be produced maybe semi-independently of U, but you get basically these two storehouses of U and V. U gets used up, V is produced, and they both diffuse across this two-dimensional system. The densities of the substrate U and V, which are now small u and small v, are represented in the simulation, which is down here. So the Gray-Scott model models the chemical reaction U plus 2V to 3V. So basically U is added to 2V and it produces an extra V. The reaction consumes U and produces V. So you have U, it gets added to a feed rate, which isn't shown in this equation, but the feed rate is basically how much U do you need to produce a multiple of V. And so that's what this is. So this is done by adding U at the feed rate F and removing V at the kill rate K. So you can also remove V from this through you have to kill V, or it becomes a sink. It basically gets used up. So both of these can be added and used in different ways. And so basically it's where you have these stockpiles where you get production that produces this thing, you get a kill rate that reduces this thing, and then U, of course, gets transformed to V. U gets used up in the service of V. This other chemical reaction, V transformed to P, is where V gets turned into a product P. And so P is an inert product, which can be, basically something akin to thermodynamic entropy, where it gets basically locked up like bond energy and it can't be used. It does represent work of V, but the important thing to remember is V is not available to diffuse. In this case, the parameter K controls the rate of the second reaction. Both substances diffuse over time at the diffusion rates d sub U and d sub V. In the simulation below here, d sub U is double d sub V. This ensures that patterns can actually form, and then you can control the feed rate and the kill rate in the simulation. So this is the simulation. This is the color here. The feed rate is here. You can modify it. The kill rate is here. So basically, if I have a high feed rate and a low kill rate, and then I get this, speeded up to like 3x, so we can get this moving. And then we start the simulation. And it doesn't look like anything's happening. So like, what do we do? Decrease the feed rate, increase the kill rate a bit, and speed it up a bit. Okay, we overshot again. Let's see. Let's go down to the kill rate of about 0.01. Sometimes these parameters have to be pretty small to get these things to work. All right, there we go. It does converge pretty quickly. So let's try this. Okay, so it's just the circle that's expanding So let's do this. Let's increase the feed rate to about that. Okay, now we're starting to get some internal structure. The feed rate is about 0.126, the kill rate is 0.01, and actually now you get a stable pattern that emerges. So you get a feed rate that's maybe an order of magnitude higher than the kill rate. I guess that's what it would be. And then that's what you get. You get this stable pattern that's fluctuating. If I increase the kill rate more, that pattern starts to change. And if I increase the kill rate over like 0.04, it basically kills my pattern altogether. So this is the feed rate. It's higher than the kill rate, but still you get these patterns. And if I increase the feed rate even more, then this pattern really starts to you can get the entire black area to segregate out. Well, it doesn't really stay that way. Okay, it's something like this. So this actually okay, now it's stable. So this actually looks like something you might see in the Belousov-Zhibtinsky reaction, or the BZ reaction we talked about in the main meeting, that you get these sort of patterns. Now it's stable. You get these I don't know what you'd call them, these little segments in the soup. And so this is stable, a feed rate of 0.187 and a kill rate of 0.023. So it's interesting to play with these parameters and see what differences you get. One of the takeaways from this is that depending on the kill rate and the feed rate and the combination of the two, when you run it through the equations of this model, you can see that there's a large amount of variation in the output. On the other hand, you can blow it out pretty easily. You can if you increase the feed rate probably over 0.2 and the kill rate over 0.04, it ceases to really do anything. So it's really interesting how these parameters get tuned. They have to be pretty low generally, but the feed rate has to be higher than the kill rate. That makes sense, because if your kill rate is just like your entropy, so it needs to be a background number with respect to the feed rate. Feed rate needs to be high to keep the system supplied with energy. So this is a nice little, this is the theory here below. So this is the differential equation, a couple differential equations. So you have this is basically I think it's a partial differential equation, as you see with the Turing morphogenesis. And this is the setup for it. So you have the feed rate here. You have the kill rate, which is here. So this one is death, this one is birth. And this has a lot to do with, and I think in particle Lenia, they brought up the idea of predator-prey equations, or it could have been one of the other papers where they talk about predator-prey dynamics. And so this is essentially that. In predator-prey dynamics, you get the birth of two different species. They have a birth rate and a death rate. And so you have to, when you play around with the birth rate and death rate, you get a pattern of predator-prey coevolution, where if you increase the amount of predator, you decrease the amount of prey, but then as the number of prey decrease, so does the number of predators, and that cycle can continue ad infinitum if they're in equilibrium. And the trick is finding the equilibrium values, and that's kind of what I was doing here. With the feed rate and the kill rate, I was trying to find the equilibrium point. The feed rate being analogous to reproduction, the kill rate being analogous to death in the predator-prey model. So that's a little bit about the Gray-Scott model. Then we can talk about particle Lenia. So this is the Google research paper for particle Lenia. This has video associated with it, so it kind of shows the, how this works. So I can just mute it. This kind of goes over particle Lenia and the different patterns. So these are the little cells. They have simple rules, so they can divide, combine, or actually I think they're just dividing in this case. And you can see that they observe these simple rules. So they divide, they form these morphologies, these clusters. They're coming from the edge, I think. And, you know, it looks almost like an amoeba or something like that. Maybe like a Volvox moving around. These aren't real species, they're just creatures that they're creating. They can create other things like oscillators, where there's an interior part of the cell, there's an edge, there's a potential energy field that you see. And these are just like based on the rules. So the rules are creating these Fa energies or these Fa forces. And it's producing things that are lifelike. It's producing things that are like how forces act upon the cell. Now these are gliders, and these are the things you find in the game of life. In particle Lenia, there's a version of the glider that you can identify. And so these things are actually pretty itinerant. They don't stick around that long, but you can observe them in the system. So now this is a steerable glider where it's bouncing off the walls. It's really interesting stuff. There's a demo here that you can download that shows you these. Yeah. So I think that's a good example of kind of the things that we have here. These are mathematical life forms. Let's consider a simple idea. Matter consists of tiny, constantly moving particles which attract each other at close distances but repel when they're too close. We can use Lennard-Jones potentials as one possible mathematical formalization of this. In spite of the apparent simplicity of microscopic dynamics, at large scales, these rules give rise to a plethora of complex phenomena, such as aggregate states of matter, thermodynamics, acoustics, hydrodynamics, and turbulence. In scientific and engineering practice, we can often abstract microscopic details behind macroscopic models. So we can use things like diffusion or the Navier-Stokes equations that operate at the scale of interest. So we can use these types of things to sort of get at, you know, if something is operating at the single cell level or the level of the external environment or the level of this little colony, we can use different models to model these phenomena. So we've talked about multi-scale modeling in past meetings, and this is kind of where that fits in. So this is smooth life. This is a continuous cellular automata. Do some really interesting things with this. There's Lenia, and then there's flow Lenia. So flow Lenia actually tries to work around the issues that Lenia has with conservation laws. So Lenia often has observed explosive growth or extinction behaviors. We talked about explosive growth being a consequence of runaway positive feedback. And so we want to try to regulate some of these systems a little bit better. Sometimes that's partially because they're, you know, the laws of physics aren't fully modeled in these systems. But we actually do use partial differential equations here, as we do with some of the reaction-diffusion models. But you still, you know, you have problems with like the conservation of energy and being totally consistent with that. So flow Lenia tries to work around this by formulating the partial differential equation system around a flow field that moves the distribution of matter in space without creating new mass. So it basically is trying to, you know, specify these conservation laws a little bit more. Then in this paper, they also propose a method of combining multiple update rules in the same space. Particle Lenia can be seen as another perspective on the flow Lenia model. We represent moving matter as a population of particles rather than as a scalar field. So that's interesting. You can actually implement this as a field-wide phenomenon. In a lot of simulations, we do that, but that ends up allowing you to treat it as a uniform force. So you can have a uniform set of forces across your simulation. In this case, it's you know, a property of the particles or a property of a population of particles. So you don't necessarily have this aspect of the uniformity. It can be more heterogeneous. So they have this stub Lagrangian flow versus Eulerian. So this is Lagrangian versus Eulerian specification of the flow field. In classical field theories, we use a Lagrangian specification. So we look at fluid motion where the observer follows an individual fluid parcel as it moves through space and time. plotting the position of an individual parcel through time gives us a path of the parcel. So this is like, if you've ever seen Lagrangian coherent structures and some of the analyses that come out of that, it's where you have an initial particle with an initial state, and then you track that particle across its evolution. And sometimes you're tracking two particles as they diverge. So, there's a whole set of equations here, but to make this simple, you have an initial condition, which is a particle, and you're basically tracking its position through time. And so this is the time evolution of this particle. I'm on 5, actually. Okay. So this is the, to make things simple, you have this initial condition, this particle here. You have the time evolution. The particle ends up here over this time. So there are physical forces acting upon it. But oftentimes in the Lagrangian formulation, you're just interested in a uniform set of physics, and you're just interested in this trajectory. You might have another trajectory here in Lagrangian coherent structures. You're interested in some of these divergences between the particles over time. So there are ways that you can calculate that, and then if they end up in like a ridge or some other cluster, that means that they've all evolved sort of along the same set of trajectories, and so then you can make that calculation and explain that there's been this diffusion of particles over a certain amount of time in a certain direction. Now, you could actually use another method, which is to look at the evolution of these particles as a property of the forces and things like that. And that is more around this Eulerian specification of the flow field. So the Eulerian specification is a way of looking at fluid motion that focuses on specific locations in the space through which the fluid flows as time passes. This can be visualized by sitting on the bank of a river and watching the river pass a fixed location. So in this case, in our space, these arrows represent these fixed locations, and you just record what's going on at those points. And so you're not calculating the trajectory from T0 to Tn, you're calculating them at different points. And that gives you this sort of heterogeneous view of things. And then, so the Lagrangian and Eulerian specifications of the flow field are sometimes loosely denoted as a Lagrangian and Eulerian frame of reference. So they're different frames of reference for this. However, in both the both the Lagrangian and Eulerian specification of the flow field can be applied in any observer's frame of reference, in any coordinate system within the chosen frame of reference. So they're different frames of reference. One is sort of at the end of the process, the other is during the process. And those are different points of view, sort of, how you choose to look at the problem. However, you can use a common set of coordinates for either, set of conditions or either, set of points of view, and it doesn't matter. It's invariant to that. But we do have this, so we're using this Eulerian specification as opposed to the Lagrangian specification. So that's I guess a summary of some of this stuff they're doing in flow Lenia and particle Lenia. Is a really interesting approach. There are quite a few well-known particle-based artificial life simulations, including the classic Boids, primordial particle systems, and many others. So this one, primordial particle systems, comes from this paper in 2016, how a lifelike system emerges from a simplistic particle motion law. So this is kind of going through some of these individual things that, this sort of model. So Boids is a model of collective flocking amongst these virtual birds they call Boids. This is a basically simplistic particle motion law. So it's very similar to that, but it gives you these lifelike forms. So self-structuring patterns can be observed all over the universe, from galaxies to molecules to living matter, yet their emergence is waiting for full understanding. We discovered a simple motion law for moving in interacting self-propelled particles, leading to a self-structuring, self-reproducing, and self-sustaining lifelike system. So these patterns emerge, they resemble living organisms. It's always about resemblance. We can't necessarily verify whether these things actually have anything beneath. And in fact, that's the idea. It doesn't have to have like internal mechanisms. It doesn't have to have consciousness or sentience or any of that. It just needs to look like a lifelike system. And so in that sense, we can use basic physics to do this. But this is again, just describing these rules of interaction. The generality and simplicity of the motion law provokes the thought that one fundamental rule, described by one simple equation, yields various structures in nature. It may work on different time and size scales, ranging from the self-structuring universe to the emergence of living beings, down to the emergence of atomic formation of matter. So it's also important to have this sort of universality aspect to it. And so they provide pseudocode, but they show there's collective behaviors for these particles and densities. You can see that there are these different patterns that we've reproduced in the Gray-Scott model. There are different types of pattern formation that occur just out of these particles and physical forces acting on them. There's no magic, it's just the interaction of forces. And so this just gives some examples. These are some more examples here of spontaneous emergence and expansion of lifelike structures into a density regulated ecosystem. This is where you have this these different biological rules such as division, growth of the population, expansion, and sort of how the whole habitat is covered by these particles. So it's kind of reached its limits of expansion. So we can do all these sorts of things that are kind of lifelike in their sort of nature, and we can actually produce lifelike behaviors. And so there's a lot of mathematical modeling in here for like density dependent growth and things like that. This is still in a two-dimensional space, but at least now we have these different conditions that are kind of like what life experiences, and we can actually reproduce these behaviors. So there's a lot of sort of state dependence. So oftentimes you're starting from an initial condition and you're moving towards some sort of self-organization, but it's always dependent on the initial condition, as we saw in the Gray-Scott simulations, that it's hard to sort of get the initial conditions right. But then when you do, you can often find equilibria where things persist for long periods of time. And so, this paper is, I'll post these papers in the Slack, and we can talk about them more. And hopefully this inspires people maybe to do some really interesting work. So thank you for paying attention, and I hope you learned something. Okay, well, if there are no other comments, then thanks for attending, and good luck with your weekly GSoC activities, Himanshu, and talk to you next week.